Hi there. Hi there. I want to show you a quick demo of the project I was working on. So my goal is to compress Capelli environments into recurrent neural networks. So here I have my environment in which I've painted walls. I've generated random textures for each wall and mapped them. And so here I have two opposite walls with the same color, so it allows for some aliasing in the environment, so certain textures are repeating. And here I have a simulation program that loads two different models. One is called the image tokenizer. It's a vector quantized variational autoencoder. Given an image, it runs this convolutional neural net to make a sequence of integers, and given a sequence of integers, it makes a image back so it can perform encoding and rendering. And there's a recurrent neural network that is a 3-layer LSTM that performs autoregressive language modeling in those image integers. So for each image I have 16 integers, and before each image in my environment I record 3 million observations of twist commands and images themselves. So my language model is trained on a sequence of a twist command followed by 16 integers describing a frame, followed by the next twist command, and so on and so forth. So this way I have a model over actions and observations. And let's see how this worked out for this particular simulation. Once again, I've collected 3 million observations and I've trained the tokenizer for about maybe a day and a half. And I've trained the RNN for roughly maybe like 20 hours total. And now I'm gonna run the program I was showing to you. So I'm starting in a pre-selected frame. Here it is in front of the vase, and I'm gonna use arrow keys to send twist commands to the recurrent neural network. So here I am, I'm moving towards that green wall. I'm moving towards this green wall past the pole. I keep moving. If I turn left, I am gonna do a U-turn, and then I'm gonna go back. So see, there's some aliasing going on because I was seeing this vase right here, and then it turned into the pole. So the network is uncertain because there are green parts of the environment in both directions. So the network can get confused. So one way is to resolve the confusion is to anchor. So here I'm kind of anchoring to this red blue wall, and if I can get very close to the wall. So here I'm holding the up button to make this thing walk as close to the wall as possible. You see the animation is a little bit blurry, and I'm gonna be turning. And here I'm resolving the aliasing to this striped wall and on the back. So we've teleported. I'm gonna turn a little bit, and then we see the yellow wall. It's turning green. And now where are we gonna teleport? And we're near the blue-green wall again, so we're here at this corner. So we're rotating around a green wall, and it looks like we've teleported to this corner right here. So there's a lot of teleporting going on, which might need to be resolved by some extra data, because this recurrent neural network did not learn a lot of context. At first I was training it with 256 steps of back propagation through time, then 512, then 1024, then 248, and this model is actually trained on 496 steps of back propagation through time, and it's still susceptible to teleporting. So in the future I could look into formatting the dataset better because I was pretty sloppy about it. There are like 17 frames per observation, one for twist and 16 for the frame. And when I was doing batch cutting for say 512 BPTT steps, I did not begin every sequence from an actual frame boundary, so maybe that could have impacted the training. I can add more dropout. I can add more data. However, overall, I'm pretty happy that the first experiment is even rendering, and looking forward to mastering the art of environment compression. So please check out my report. It's been a fun project, and see you later.